I think everyone knows the topic, but so I would like to thank very much the organizers for the invitation and giving me the opportunity to present my talk today. So I'm going to actually highlight the new advancements in front tracking based numerical simulations. But before that, I would like to give credits to my students, because I do remember every time James Gleam was giving a talk, and when he was giving us credits, I was very happy. So basically, I have 6 PhD students, and Irina is working on the large simulations around the buildings. But today I'm going to highlight the talks of the research that we are doing together with James, Sean, and Ryan. So we are still, most of the work are still in work in progress. And so basically we are looking at like extending the existing front tracking method with the AMRX, which is the block structure adaptive mesh refinement techniques. And Ryan has been working on the numerical simulations of Richmar-Meshkov and also exploring the higher order Vino schemes. And Sean is also doing some work and specifically on the physics-informed neural networks. And I will put together some of those talks together. So I think since we are running out 15 minutes late, I don't want to actually introduce at all the turbulent mixing, but one of the images that I really like was the middle one, because it is called accidental painting, where the white paint, which is the dense one, actually pour onto the black paint. And I just love that image. And so basically, we are going to look at the turbulent mixing due to the Rayleigh-Taylor instability and Richmar-Meshkov instability. I'm not the experimental, so basically what I will be doing is focus on the modeling and simulations, and also validation, where validation is basically comparing our numerical results with the experiments also. And we will go back and see look at the effect of the input parameters, model parameters, and we will also do talk about the quantification, uncertainty quantification. And so basically, we have some issues and challenges in these simulation and modeling of our Rayleigh-Taylor, of the Rayleigh-Taylor Richmar-Meshkov instabilities. So Schilling 2022, which is one of my favorite papers, actually he lists all these issues. What are those issues? We have non-unique definition of mixer layer width and self-similar mixing. So our interest is in Rayleigh-Taylor finding these mixing layer growth parameters for bubbles and spikes. And we actually use Edwood number, and we know that there's a dependency of those growth rate parameters on the Edwood number. So there, I just listed 3, but there are more, such as Lubescu uses some other definition of these mixing layer growth rate parameters. And what else? When we are doing the analysis, experimentalists only cut off the 1% of the bubble heights and the peaks and so on, whereas from the numerical point of view, there's a cutoff, higher cutoffs as well. I'm sorry, vice versa. Many experiments use the 5 to 10% cutoffs. Many simulations use 1%. And again, this alpha bubble growth rate for bubbles is weak function of the Edwood number. Alpha spike is a strong function of the Edwood number. And another issue that we have faced is the initial perturbation, how the perturbation has to be like random amplitude, standard deviation as well. So while experimentals have both initial density and velocity fluctuations, most of the time simulation we use one type of perturbation. And as well as boundary conditions, computational domain, and closure modeling, where the closure model in large eddy simulations using explicit, implicit, subgrid scale model. So actually we answer most of the questions in my past work. So basically what we do see is, I didn't connect, I don't think that this will work, but, oh, it does, okay. So what do we see in here? Flash code. On the left-hand side, we do see the flash code, and this is basically a single mode Richmond mesh Rayleigh-Taylor instability at time equals to 10. And this is, we actually have used the front tracking and created an application programming interface for front tracking and run flash code with it. So we see that a diffusive interface and Schaff interface. And then we look at the initial perturbations where we want to answer could be like long wavelength perturbation present in the initial data. The answer is yes. And could contribute to the self-similar growth by a factor of 2 or more. And the answer is no. These are the findings that we had done using model analysis of the experimental data. So we took the experimental data at plate 3. We actually propagate back in time, get the initial estimation to the input parameters using model analysis and as well as Fourier transform. And then we did the prediction, and then we use these initial conditions for our simulations, and we compare our numerical results versus the experimental data of Smith and Young's. And Smith and Young has immiscible, miscible, so we did lots of experimental studies. And we also did some convergence studies, which is called W-star convergence, so a Young measure valid solutions. What we did is we see 3 mesh level in here, coarse grid, medium grid, fine grid, and we look at the heavy fluid concentration. And these simulations are 3D. We took a plane, mid-plane, and we look at the late time. And then we extract the probability distribution function, and which we call it PDF, and we bin these values, and we create those supercell grids that we see in here. So basically, we do have 8x2 supercell grids, and for each supercell grid, again, we bin the concentration values, and we make comparison between the coarse grid and medium grid, and then we make a comparison of the medium to fine grid and look at the cumulative distribution functions and to see if there's a convergence in these PDFs and CDFs. And we didn't see any convergence in the PDF, which we said, okay, we need further investigation maybe. But we started to see some convergence in the CDS in L1 norm. And other study that we have done is the uncertainty quantification. So we wanted to actually look at the input parameters in the simulation in Rayleigh-Taylor. So what we do see in here, the black dots, these are the experimental data, and the idea is we have a set of parameters, and we use a Sandia National Lab uncertainty quantification toolkit, which is called UQTK, to do forward propagation and do sensitivity analysis as well. And we find out that the initial mass diffusion layer has the most effect on the numerical simulations. And I think this was one of the most challenging projects that I have worked, and that was the turbulent combustion, which was a collaboration project with the Stanford University. So basically, there's a hydrogen coming in from the nozzle, and there's the oxygen, and they have 8 species 21 reactions, and you solve the reactive Navier-Stokes equations, and you actually calculate the production rate of these pieces in the concentration equations and so on. But what we do see that we see the OH concentration and H2O concentration, where OH concentration defines the flame of that. And all these simulations that we have done are extremely computationally expensive. So we need to take advantage of the supercomputers. So at that time, we had the 2011 and 2012 DOE Insight Award to do all these uncertainty quantification, W-star convergence, and use the IBM Blue Gene machine at Argonne National Computing Festival. And recently I visited that lab, so I also saw what is coming next in November, and I was very excited because Auro is coming, and we will see if this is going to be the top 1 supercomputer in top 500. So these are all, I tried to actually wrap everything up what we have done in the past in terms of turbulent mixing and turbulent combustion. And so all these, we achieve excellent agreements, good agreements in terms of comparison between the experiments and the simulations. So what was the numerical approach that we used? We used large eddy simulations, and we resolve to certain scale. We model the small scales using dynamically Smogorowski schemes, subgrid scale model, and as well as front tracking. So the governing equations and the simulation approach that we have, the governing equations is the compressible large eddy simulations, which are the filtered Navier-Stokes equations for multi-phase flow. So the idea is simple. There are 2 filtering. One is grid scale, and so this is just an example to show how the next slide we will see the entire equation. So basically the Fourier filtered continuity equation, we apply the grid scale first, and this grid scale is denoted by the bar, and then we apply the density weighted filtering, and when we apply the density filtering, we actually get a Fourier filtered continuity equation. So overall, in the next slide that I will show, we will see tilde. Again, tilde represents the density weighted filtering, where bar is representing the grid scale. So these are the equations that we used. Of course, for the turbulent combustion, we have different equations, reactive Navier-Stokes equations, where the concentration equation had the production rate as well. These are the equations that we use for the Rayleigh-Taylor instability. So I'm not going to again talk about all these density, momentum, energy. I mean, we solved the momentum equation, energy equation, and as well as the concentrate equation. But what I want to highlight in here is we have some subgrid scale terms that are denoted, it's supposed to be blue, but somehow, so these are the subgrid scale terms that we see. So the dependent variables that we have are the density, concentration, velocity, pressure, and energy. And the energy is represented in here. So we also have the viscous stress terms, where we see the filter dynamic viscosity. So again, the subgrid scale in basically in here we see these variables, and those variables are in the momentum and energy equation. So we look at those different. So the best part of this is these models are parameter free. Basically, we determine the proportionality of those coefficients dynamically from the simulations. So everything that I have talked is in the front tracking method. It's a multi-phase package, so it's multi-physics package. It supports MHD as well. So equation of states, we have a bunch of equation of states, including Helmholtz, like the stiffness EOS and so on. We have fourth order Runge-Kutta time stepping. And so we actually recently go to the higher order Vino reconstruction, and we're also working on the AMRX, like the expansion of the front tracking methods with adaptive mesh refinement techniques. So basically, the front tracking is providing us a sharp resolution of fronts. And how does it do it? It's actually it's based on the it solves enforces jump discontinuities. So again, using the discretization of the earlier invariant variables is conventional using Vino. So we have to make sure that if there is for stances that has the front, which cut by the front, we extrapolated the ghost cells values used to complete the stances so that it contains states from the single side of the entire phase. And it has some hypothesis. It builds based on the hypothesis, and we have to make sure that also it's uniquely defined by its intersection with cell block edges. So this is also a reference to the paper. So we want to explore the effect of the higher order Vino scheme. So, and also I wanted to study new Rietzschmeier-Meshkov's instabilities. So in the community, what is common is earlier questions are solved. So the earlier questions with the mass fractions. So we do have the state variables, and again we define the specific internal energy, and for the closure of the system. And so once we have the implementation of this higher order Vino schemes, there are two benchmark tests that we test. One is the 1D solved problems, and where we see the rarefaction, contact discontinuity, as well as the shock. And what we want to do is we want to go coarser in mesh, reduce the computational time, and also increase the order of the accuracy. So we are comparing in the zoom to this contact discontinuity is we are comparing the fifth order Vino scheme, front tracking with Vino scheme, using 200 mesh points, and as well as ninth order Vino scheme with 100 cells. So we get actually very close answers. And then we look at the test problem again, Schuh-Osher's test problem, and to check the stability and the accuracy of our Vino scheme. And again, what we observe that the fifth order 1,600 mesh that we see with the blue, and the ninth order 400 mesh, and as well as ninth order 800. So the goal in here is our computations are very expensive, so we want to have a coarse grid using the higher order Vino scheme. So what we do see in this table is the ratio of the CPU time at time equals to 1.8 for the shock entropy wave interaction. And we look at the ratio between the fifth order. That's why we see 1.0. So these are the ratio of the CPU time, and I highlighted in bold to say that, okay, ninth order 400 mesh points is 0.4 times cheaper comparing to the fifth order. So if you talk with Schuh, and he has also a very good review paper, which I should have Schuh 2020. So he actually has a so he suggests to beginners to use the classical fifth order, and then we use actually a ninth order coming from the Balzara and Schuh papers. Not to test like the toy problems, but we want to actually perform front tracking, Rietzschmeier-Meshkov simulations, and do comparison with the experiments. This time, the experiments that we take is Collins and Jacob 2002, which is used as a benchmark in our community. So on the right-hand side, we see his experiments. On the left-hand side, we see our simulations. So we initialize the initial density profile over the diffusive interface, and also we set up all these boundary conditions streamwise direction, inflow and reflection, span-wise in periodic. And we defined like in this growth rate, what is the important thing that we need to look at is we look at interface velocity, and everything that is noted with plus are after post-shock quantities. We use those values to make a prediction of the growth rate of the Richmond-Meshkov instability. And then we see a comparison. So we actually didn't observe excellent agreements for the first time. And the reasoning behind that is the experiment has 2 slots, which the simulation doesn't have. So the discrepancy in the interface velocities are due to these 2 open slots in the test section of the shock tube experiments. When the incident shock passes through the slots of the experiments, it creates expansion waves, and we believe that it slows down the interface velocity in the experiment. And so then we look at different Mach numbers, and in early time we have an excellent agreement for Mach 1.11, and we do have some discrepancy for Mach 1.21. And so the objective in here is performing high resolution and high resolution, higher order simulations to actually model these single mode Richmond-Meshkov instabilities. And so these are the results that we are seeing. Again, what those numbers are. The first represents the order of the Venus scheme. The second numbers are representing the number of the mesh points per wavelength. And this wavelength, 512 per wavelength, is pretty fine grade. We see that, yes, going higher order is improving and so on. So, and this is we see these late time after reshock, we see some overall agreement between the experiment and simulations. So, and then I wanted to also perform some new Rayleigh-Taylor instabilities, and with the idea of comparing our simulations with the theory that is recently presented in 2023 paper of Obarzi, and they are looking at the variable accelerations. So we set up some simulations based on the simulations that are performed on the paper, and also the amplitude in the initial perturbation, and we also vary the Atwood numbers. So this is a ongoing research. So what we do see is in the blue is the finer and the coarse, like one level coarser. So we see the entire face blue, which is the fine, and as well as difficult to see maybe the green one. So the amplitude in terms of the penetration distance of the heavy fluid onto the light fluid is except the tip is slightly different, and we also look at the velocity field around the vertices. And while I was listening Osher's talk, I said maybe I should put something about machine learning, because this is something that we are also exploring. Can we learn from the data, and actually can we do physics-informed neural networks? So basically, this is again something very new to me as well. So Carneades has this physics-informed neural networks which take into account the PDEs. So what we do see in here is the physics-informed neural network. So basically, all these shock and contact discontinuities after such an iteration, it's not doing well. So we are also looking at entropy, shock entropy problem. And so I think I will finish, because I will finish on time. So I would like to thank all my senior colleagues who helped me for providing me very helpful comments and discussions from the experimental points of view, and also expanding. So thank you very much.
Questions? I have a question. In one of your examples, in the 1D case, I think it was salts, you wrote it's contact discontinuity tracking.
Oh.
So do you track the contact discontinuity? And if you do, why do you still have dissipation, like diffusion, smearing out?
I mean, I could definitely have more. If I refine the mesh, I will get exact. So here I use coarser mesh using the front tracking method.
Oh, so are you front tracking the contact discontinuity and impose the jump conditions there, or?
I mean, we use the front tracking with the like Rangnick-Huguenot conditions, and we also use for the left side and the right side, we use the Vino scheme. So this is a pretty coarse grid that we have.
But if you do impose the jump condition at the contact discontinuity, why doesn't it remain sharp?
So the sharp one is, the black one is the exact solution.
Yeah, but why do the numerical solutions then smear out?
So again...
because you use Vino over the entire discontinuity?
But Vino handles the discontinuity by taking the weights zero around the discontinuity. So like that smearing out is due to the coarse grid resolution.
We'll talk later.
Okay.
Other questions? One more. Yeah.
Yeah, I think I missed like most of like what you say about your neural network. So can you describe a little bit more? You use like how is like your layers? Like what do you use as like as an input, and what do you like? What is like the game to using a neural network?
Oh, neural network. Oh, okay. I mean, so we do have bunch of simulations, and the idea is to make predictions from the data. And for instance, what we do see in here is the reference solution, and this is coming from the data assimilation. So using the data, making a prediction. So basically, the whole idea is making predictions or based on the data that you have without doing the real-time simulations. And because can we make predictions? And this is basically comparing the this is the pures, like the numerical simulation, and this is based on the neural network. You train the neural network to find the optimal parameters for optimal parameters to minimize the loss function, and this is basically just coming from the data analysis. Yeah.
Where do you?
What is?
How good is this for the prediction?
It is horrible. It is terrible, and that's what Osher was saying as well. So, physics-informed neural network is not doing well around the shock discontinuity, and the idea is we are working on different type of segmentations and learn from those regions and so on. So.
Just one remark. It can be just a medical, not real physics. It's very often that we have some kind of oscillations around.
So this is basically the physics-informed neural network answer. So this is and this is the solution coming from the our solution. Yeah. So this is doesn't capture those N waves, the transition waves, and as well as the shock location is even wrong.
So intellect is better than artificial.
Yeah.
Okay, and let's close it with that statement. Thank you all.